for HL93 live load. The span length of the bridge is 35 feet, center to center of bearings. Center to center of bearings. Okay, bearing means from the bearing plates. And the width of the bridge from curb to curb is 44 feet. Allow for a future bearing surface of 3-inch thick bituminous overlay. The concrete strength is 4,000 psi and steel is 60 psi. Now look at this bridge on the right. I will simplify this a little bit so that you can see this. This is the bearing. So from the bearing, the span length is 35 feet. Okay. This is the center line of the bridge. Width, the interior width of the bridge from curb to curb is 44 feet. This is the roadway on which the vehicle will run. And the exterior, including this 15-inch curb, is 46.5 feet. Okay. The future bearing surface of 3 inches also included, shall be included in the design. It is the thickness of the slab. Okay, we will start now designing this slab bridge. The span length of the bridge is given as 35 feet center to center. The clear roadway width is 44 feet curb to curb, is shown in the figure. Now for a curb width of 15 inches, total width of the bridge is 44 plus 2 into 15 divided by 12 is 46.5, although it is given in the figure. Minimum thickness of bridge slab is given by formula 1.2 s plus 10 divided by 30. S is 35, 1 plus 1.2. This gives us 1.8 feet or 21.6 inch. So a 22-inch thick slab shall be provided for a span of 35 feet bridge. Okay. With this slab thickness, we will calculate the slab load 22 divided by 12 into 0.15. So it will give us 0.275 kip per square foot. Bearing surface of 3 inch will give us 3 divided by 12 into 0.14. 0.14 kip per cubic foot is the density of bearing surface. So this is 0.035 kip per square foot. And dead load moment, slab moments, WDC is square divided by 8. WDC is 0.275 into 35 square. This is the slab bending moment, 42 foot kip per foot. The bearing surface bending moment is 0.035 into 35 square. It is 5.3 foot kip per foot. Live load movements. Live load movement, as discussed earlier, will be obtained by placing the middle axle in the mid span of the bridge with equal spacing on both sides of this for front and rear axle. So this we can draw shear force and bending moment diagram for this simply supported line element, and this gives us a bending moment of 350 foot kip, which is a bending moment coming from the line analysis. You should note and understand this. For a tandem, we get a bending moment of 372 foot kip, which is greater than the truck load. Lane moment is 0.64 into 35 square, it is 98 foot kip per foot. We will take now, we will take the maximum bending moment for the two vehicles is coming from for tandem. So we will use tandem bending moments instead of truck tandem bending moments. And we will also apply 1.33 factor to the tandem bending moments in order to include the effect of vibration or impact. So 1.33 into M tandem is 372 plus M lane is 98. So this gives us 593 foot kip, but for line moments. This must be divided now by E to take to convert this bending moment of the line to two-dimensional in order to include the two-dimensional effects. And for this, we will calculate the single lane loaded E and multi-lane loaded E. The single lane loaded E is 10 plus 5 into L1 W1. L1 is modified span, minimum of S and 60, so minimum is 35. And modified edge to edge width W1 is minimum of W1, which is 46.5 or 30. So we'll use 30. So while when we substitute the values of L1, W1 in this equation, 35 and 30, we get a E value of 172 inch or 14.3 feet. For a multi-lane loaded, repeating the same exercise, we take E is equal to 142 inch, which is 11.84 feet. And as was discussed in the previous slides, that the least of these two E will be taken in our calculation. The least is 11.84 feet, which is coming from the multi-lane loaded equation of E. So now we will divide our bending moment by this E. The bending moment, which is 593, will be divided by 11.84. So this gives us a bending moment of 50 foot per foot. Now we will calculate the amplified bending moments. 1.05 into 1.25 MDC. MDC is the dead load moment. MDW is the bearing surface bending moment, and this is the live load bending moment. 1.75 into 50. This gives us a bending moment of 155.3 foot per foot. When we convert this into inch per foot, we'll multiply this by 12 and we will get 1863.6 inch per foot. Now we can design this very easily. The bending moment is 1863.3 inch per foot, and the effective depth of the bridge slab, we know that the total depth is 22 inch. Will provide a cover of 1 inch minus half diameter of the bar which we will use. So let's say we want to use number 8 bar in this bridge. Then the effective depth is bottom cover for slab is taken equal to 1 inch. If the effective depth is if the bottom cover is taken as 1 inch, then D is equal to 22 minus 1 minus half of 1 inch. This gives us the effective depth of 20.5 inch. AS minimum, we know that it should be 0.0018 into A gross. A gross means 12, which is the unit width, and 22 is the depth of the bridge. So this gives us 0.47 square inch. Our minimum, our reinforcement shall not be less than this. And if we use this hit and trial equation, A is equal to MU divided by 0.9 FYD minus A by 2. With the small a, let's in the beginning we assume 4 inch or 5 inch. Then we can calculate AS for this MU, 1863.6 inch per foot. Okay, Fi is 0.9. So after 1 or 2 trials, you will get some reinforcement AS as you have done in the case of building beam design. Finally, we get a area of steel equal to 1.8 square inch. If we want to use number 8 bar, whose area is 0.8 square inch, we will require number 8 bars to be placed at 4 center to center. Distribution reinforcement or bottom transverse reinforcement, according to the H2 5.14.4.1, the amount of bottom reinforcement may be taken as a percentage of the main reinforcement required for positive movement as follows, but not less than shrinkage reinforcement. 100 divided by S. S is 35. 100 divided by square root of 35. It is 16.9%. And 50%. So 16.9% is less than 50%, we will use 16.9% because the least value shall be used. And 0.169 of the main reinforcement. Main reinforcement is 1.8. So 0.169 multiplied by 1.8 gives us a value of 0.304 square inch. But then we should compare this value with the minimum reinforcement. And the minimum reinforcement is 0.47 square inch. We will use the minimum reinforcement as transverse bottom reinforcement, which will be placed at 18 center to center if we use number 5 bar. Similarly, the top transverse in longitudinal reinforcement will be also placed according to the H2 code. The maximum spacing for temperature and steel reinforcement in one slab according to this is minimum of this 110, 18. So also a top reinforcement in transverse in longitudinal reinforcement will provide number 5 at the rate of 18 center to center because it is also the minimum reinforcement that we have calculated for bottom transverse reinforcement. So finally, what we will do is that we will provide number 8 at 4 center to center is bottom main reinforcement along the span length of the bridge, transverse bottom reinforcement, perpendicular reinforcement to this main reinforcement, number 5 at the rate of 18 center to center. Since this is the minimum reinforcement which has been calculated from the shrinkage reinforcement, and according to the H2 guidelines, we will also have to provide the shrinkage reinforcement both along the long and transverse direction equal to shrinkage reinforcement. So this number 5 at the rate of 8 center will provide not only this transverse bottom reinforcement but also its top transverse and longitudinal reinforcement. Finally, the bridge reinforcement will look like this. This is the number 8 at 4 center to center main reinforcement, which is because the section is taken along the width of the bridge. So main reinforcement will look like this: is dots, which has been placed along the length of the bridge. The transport reinforcement along the width of the bridge is this